All right, thanks, Walt. Hi, everybody. I'm Carlos Vargas. I'm faculty at Stewart Observatory in the Department of Astronomy here. Today I'm going to be talking to you about Aspera, which is frequently mispronounced. The emphasis is on the first A, excuse me. But I'll be giving you all a status update on where we are and a little bit of background on what the mission is and what we are aiming to do. But before I get into that, I'd be remiss if I didn't extend a big thank you to UASI for tons of support at the proposal stage and continuing throughout. Thanks to Betsy Cantwell, Hot Bailey, Walt Harris for some wonderful long conversations over the last couple of years. So really appreciate all the support. Okay, so Aspera's mission is to be the first to detect and map in a volume-filled fashion the warm, hot circumgalactic medium in emission. So what the heck does that mean? Well, the circumgalactic medium, or CGM, is shown diagrammatically in an artist's rendition on the right-hand side of this slide. So if you were to take your favorite optical telescope in your backyard, point up at a galaxy nearby to us, or even pull some Hubble Space Telescope optical images of a galaxy, all you would be seeing is the star-forming disk of that galaxy, where all the stars live in that central 15 kiloparsec or so region at the center of this image here. But in reality, invisible to us in optical wavelengths, galaxies are undergoing this beautiful cosmic dance, balancing inflowing gas with outflowing gas originating from the disk itself. So high energy processes from high mass stars like stellar winds and supernovae are very good at ejecting matter outside of galaxies, along with supermassive black holes at the centers. Active galactic nuclei in galaxies are very good at ejecting gas. Sometimes that gas leaves in outflows, other times it rains back down into the potential well of the galaxy to form future generations of stars. And all of this contributes to the high rates of star formation that we see continuing in the nearby universe for these galaxies, even though we cannot account for that rate of star formation fuel within the disks itself. So long story short, if we are to ever have any hope of understanding the way galaxies evolve over time, of understanding the matter which forms future generations of stars and in hand future planets, we must understand the details of this complex galactic gas cycling mechanism. Okay, so what do we already know about this galactic gas cycle and the circumgalactic mediums of galaxies? So to date, the vast majority of information we have about this comes from absorption line studies. I'll focus on quasar absorption line studies for simplicity here. So on the left-hand side here is another diagram showing how these studies typically work. So you have your telescope pointed to a background point source, typically a quasar, whose spectrum is somewhat well known as expected. And if you're lucky enough, along the line of sight to that quasar will be a galaxy whose CGM you would like to study. Okay, this is an incredibly powerful tool where you can study absorption features in that quasar spectrum, which come from the species existing in the intervening foreground galaxy's circumgalactic medium. So incredibly powerful. You could study things at super low density here that you could not study in emission. However, there are two major, somewhat obvious caveats to this. One, you got to be lucky enough for there to be a quasar behind the target you want to study. So immediately, that's not always the case. It's actually somewhat rarely the case for any old galaxy. And also, by definition, you're only studying point sources. So you're only studying pencil beam sight lines through the galaxy that you're interested in studying. So volume-filled mapping of morphological structures is impossible using this technique. So Aspera aims to usher in an era where we no longer need to rely on absorption line studies, where we can actually volume-filled map the circumgalactic medium in its wonderful detailed structures in emission. So on the upper right-hand portion of the slide here, I'm showing the simulated oxygen-6 emitting morphology of this warm, hot phase, about 10 to the 5 Kelvin or so in the circumgalactic medium. So that's what it might look like, again, simulation. Aspera, in our mock observations, which I'm about to show you, will be able to piece together individual slices of this galaxy over long, extremely long pointings to be able to produce a mock image that may look something like this for a typical galaxy at the distance of NGC 4631, about 10 or so megaparsecs from the Milky Way. Great, so a bit about the Aspera team. Aspera is managed here at the University of Arizona. I'm the PI, Carlos Vargas. Erica Hamden's the deputy PI. Han Chung is the project scientist, all at Stewart Observatory, along with Tom McMahon, the project manager. I won't go through all the names of everyone in the interest of time, but a few shout outs. Ascending Node Technologies is a local Tucson company that is helping us with our ConOps and software. We'll have a great talk, I think, about Spaceline in a little bit, which Ant does. Carl Hergenrother, John Kidd, and Sanford Selznick there. Sensor Sciences builds our microchannel plate detectors, Ozzy Sigmund. University of Toronto Institute for Aerospace Studies Spaceflight Labs, big acronym, for SFL. Simon Grocott is our link there. They are building our spacecraft, which if you didn't know, you can buy spacecraft off the shelf now, which is pretty crazy. And our external science team spanning NMSU, Space Telescope, Columbia, et cetera. The color coding here, which I must also mention, blue for early career faculty and postdocs, orange for grad students, yellow for undergraduates, and purple for early career technical staff. We are now over the 50% mark of early career personnel on this project. Milestones and schedule, so where are we? Aspera began officially, our first day of funding was April of 2021, April 1st, 2021. The Pioneers program, which we are funded within, has a 5-year cradle to grave requirement on our schedule. So these are at a breakneck speed. So we just passed our PDR at the end of last year, and we are right up against our CDR, which is happening next month, our critical design review here at Arizona. And at the conclusion of that CDR, pretty much right after, we will begin our payload build phase with payload environmental testing beginning at the end of 2024. So for most of the rest of this year and most of next year, we'll be building and testing. And we will be shipping our payload off to our spacecraft vendor, SFL. I'll show you a few pictures to make this all make a little bit more sense in a moment. But that'll happen early in 2025 with an expected launch date at the end of 2025, October-ish. The launch date itself, don't ask me when we'll launch or where we'll launch. I wish I knew as much as you wish you knew. But that is in NASA's court to find a ride share for us. We may know as little as 1 year out from launch. So here is Aspera, here's the payload. So Aspera is comprised of 2 identical Roland circle spectrographs in a design that's, if you're familiar with the Fuse telescope, it's basically almost exactly the same, scaled down a lot and cut in half. So light enters in the lower left in the 2 identical apertures out to 2 OAPs, about 5 centimeters, so very small, which will reflect the light to 2 finely ruled toroidal gratings, which are mounted right in between the 2 apertures there, and finally onto a microchannel plate detector, which both channels share a single unit. 2 long slit spectrographs, very narrow wavelength of regard, 103 to 104 nanometers. Spectral resolution 1500, spatial about 75 arc seconds. Both the slits will have 1 degree in length and 30 arc second width, an absurd sensitivity of 3 times 10 to the minus 19 in CGS surface brightness units, over 4.5 days of exposure, all high TRL tech, yada yada. If you want more info on the payload, check out Han Chung's SPIE proceeding. Banana for scale. So this is how large our payload is. Covered up a little bit, but we are rather small. You could fit us on a desktop pretty easily. And one of our grad students, Afaq Khan, may or may not have been stealing the 3D printed mass model or a 3D printed model during our PDR. Almost wrapping up here, just a few quick updates and fun pictures to show. So on the left-hand side here, Han Chung is doing a fit check of our flight OAPs. So we received our flight OAPs a couple of months ago now. fit check with our coating fixture, which we will apply the UV reflective coatings on those. In the middle here is me playing around with our optical alignment test bed, along with the CGH and interferometer. And on the right-hand side, a few of our team members at LPL cleaning the our calibration chamber, our vacuum chamber, where we will be calibrating the instrument. On the left-hand side, very exciting, a few of the team and myself just got back from Toronto at a visit to the spacecraft vendor, where we saw the flight qualification unit of our spacecraft. I call it our little mini fridge. It's roughly that size. You can see the aperture door, which would open upward on the left-hand side here, and the solar panels, which will wing out to the right and behind, which you can't see for the spacecraft there. And our mass model, which we ship to SFL for the qualification, where they'll vibe and TVAC it all mushed together, shown on the right-hand side there as well. So things are moving along very rapidly, very exciting progress in the last year or so. So wrapping everything up, Aspera is a far UV, Lyman UV really, SmallSat to map warm, hot oxygen-6 emission in nearby galaxies. We are one of the inaugural funded NASA Astrophysics Pioneers projects. We are entering the instrument build phase later this year after our CDR next month, with a planned rideshare end of 2025. Ops duration of 9 months, which I neglected to mention previously. But that's it. Thank you very much.